Okay, so let me switch gears here. Have we started this part? Association. This is where we left off. This is where we should start. Okay. All right, so we had finished talking about the different properties of water, and then this last concept has to do with pH and acids and bases and how that relates to water. So, so water has a pH of 7. And is neither an acid or base, and we'll talk about why that is. So a hydrogen atom and a hydrogen bond between two water molecules can shift from one molecule to the other. And we're going to write this in words right now, and then I have a picture that more clearly illustrates that. So the hydrogen atom leaves its electron behind. So electrons are negative, so it leaves that negative charge behind and is transferred then as a proton or hydrogen ion. Because it lost its electron, it left its electron behind. The molecule then now with the extra proton is now what we call a hydronium ion, or H3O with a positive charge. So it's H2O with an extra H plus. So that's where the third and the plus comes from. And the water molecule that lost the H pluses, remember the H plus left its electron behind, so the electron has a negative charge, so it's just OH, lost its H, but the electron left behind makes it negative. And that's called the hydroxide ion. We're going to see as we go through with pH, hydrogen ion and hydroxide ion, these words you need to know refer to OH negative and H pluses. Those are important with pH. So, so when you look here at this picture shows you what we just wrote about. So here are two water molecules, hydrogen bonded together. And so remember it says you can have the transfer of a hydrogen, of one water molecule that's hydrogen bonded to another being transferred. So if we look here, this water molecule here has lost the H, but remember hydrogen has one proton in the nucleus and one electron spinning around it. This hydrogen leaves its electron with this OH now, therefore giving it a negative charge. And the hydrogen that now has a positive charge because it left its electron is attracted to the oxygen, and so we have what's called the hydronium ion, or H3O, all right, with a positive charge because that hydrogen here that it just gained gives it an extra positive charge. And so, so that phenomenon, it says this process can be described in a simplified way as the separation of a water molecule into H plus hydrogen and hydroxide or OH negative ions. And this is the concentration of these relative to one another is the basis of the pH scale. So this is statistically rare that this happens. The dissociation of water molecules can, though, have a great effect on organisms, and pH has a great effect on organisms. And so if we change the concentration of hydroxide and hydrogen ions relative to one another, it can really affect a cell and how the cell works and if it can even function at all. So let's talk about pH, effects of changes in pH. So due to the fact that we just talked about that a water molecule can dissociate into H plus and OH negative, the concentrations of H plus and OH negatives then are equal in pure water. So I just drew an example up here. So 5 H pluses to 5 OH negatives concentration is equal. Then if you add certain solutes, remember solute is something that dissolves in water, adding certain solutes called acids and bases can actually modify and change those concentrations. so in pure water, they're equal, but if you add something to change that, they can become unequal and therefore can change the pH. So we use, biologists, but all scientists, use the pH scale to describe how acidic or basic a solution is. So let's see. Pure water has equal concentrations of H pluses and OH negatives. If we added an acid to pure water, does anybody know what acids do? Added to water. I'll tell you this, acids change the concentrations. All right, so here we have equal concentrations of H pluses and OH negatives. So they change that by doing something. In chemistry, did you get to acids and bases?
Yeah, a bit.
A bit. Some no and some and yes and some.
We did.
Okay. How many people did not get to acids and bases? I'm just curious. Okay, to see how many people it's new for.
Isn't that acid like more H so it's lower the pH?
That's exactly right. Acids, by definition, release H plus ions into the solution. So when you add an acid, it's releasing H plus ions. And so we had equal concentrations here. If an acid releases H plus ion concentrations, so now in comparison of H pluses to OH negatives, we did have 5 out of the 10 being H pluses, 5 out of the 10 being OH negatives. Now we have 11, and 6 out of those 11 are H pluses, and only 5 out of those 11 are OH negatives. So what did we do by adding H pluses into the solution? What did we do to the H plus ion concentration? Increased it, and the OH negative concentration decreased it. And even though we didn't change the number of OH negatives, the number of OH negative ions are the same, but by adding H pluses and looking at the concentration and like the percentage a little bit, we've lowered it by adding H pluses. And that's what acids do. So like for instance, a strong acid is hydrochloric acid, HCl. This is the hydrogen ion and the chloride ion. And remember with ionic compounds, we talked about NaCl, just dissolving in water, remember? And so what happens is when you put HCl into water, it dissociates into the H plus ion and the Cl minus ion. Because the water molecules, remember the water molecules surround it from the hydration shell, just like the NaCl. Same thing happens with hydrochloric acid. And now with HCl, increases the hydrogen ion concentration and therefore would make pure water more acidic. All right, that's the reason why. So, so that's the definition of an acid. Any substance that increases the H plus ion concentration of the solution. I'm just going to put here, it releases H plus ions. So then, a base is the opposite of an acid, so what is it going to do? It's going to decrease the H plus ion concentration. So a base is a substance that reduces the H plus ion concentration. I want to talk about how in the world it does that. There's actually 2 different ways that a base can act. So here's my pure water again. So base by definition reduces the H plus ion concentration. So here's my pure water again. What's a way that a base you think could reduce the H plus ion concentration? That's right, it can add OH minuses. So if a base adds OH minuses, now we have a higher concentration of OH minus and a lower concentration of H pluses. That's reducing the concentration. So let's write that here. It can, I'll put release. Release the hydroxide ion. Anybody have an idea of what a second way? There's another way it can reduce the H plus. Trying to reduce it, so what?
Where it bonds with the hydrogen?
Yeah, or it can bond with one of the H pluses, and so if it bonds to the H plus becomes part of the base and no longer is floating around in the solution, and therefore reduce it. All right, absolutely. And so if it bonds with this H plus now goes and bonds with the base, now you have less H pluses floating around in the solution, and you lower the concentration of H pluses compared to the OH negatives. So I'm going to put here it accepts H plus. And both of those ways reduce the H plus concentration. And so we measure hydrogen ion concentrations and how acidic or basic a substance is by the pH scale. pH scale of a solution is determined by the relative concentration of hydrogen ions. Acidic solutions have pH values less than 7, and basic solutions have pH values greater than 7. Most fluids in living organisms, the pH values range somewhere right around neutral. It's not usually at neutral, a little bit below, a little bit above, ranging from 6 to 8. And so, and depending upon the organism, the cells within the organism, we have an exception inside of the fluid inside of our stomach. We have special cells that release acid. It's much more acidic than normal. And so there are exceptions, but the majority of fluids in living things range right around 6 to 8. And it's important for that to happen. And so the reason why is because there are lots of chemical reactions that occur in your cells all the time that keep you alive. There are hundreds and hundreds and hundreds of chemical reactions going on in your cells right now that allow you to be alive right now. Does anybody know what the little substances are that speed up chemical reactions inside cells that allow your chemical reactions to occur at an appropriate rate so that you can stay alive? Because see, most chemical reactions will occur, naturally, but at such a slow rate that if they were to go at that rate, we would die before we get the products of those chemical reactions. So we have to have these substances that speed up chemical reactions. They're called enzymes. So enzymes, we're going to talk, if you don't remember, we're going to talk more in depth about them in the class here, but I'm just introducing it now. So enzymes speed up these chemical reactions, and enzymes are crucial, and they work best in a certain environment. So what does that mean? They work best in a certain pH. So it's really important between 6 and 8. Most enzymes work best between pH of 6 and 8. If it gets too acidic or too basic, the enzymes don't work, your chemical reactions don't occur, and it can be life-threatening. Same thing with temperature. Enzymes work best at a certain temperature. If your body temperature gets too high or too low, the enzymes don't work at the proper rate, and so that can also be life-threatening. We talked about with the water properties, with the evaporative cooling and sweating, that's one of your body's ways to keep your temperature from getting too hot. So, and one of the reasons is because of those enzymes, they need to have a certain temperature. And so, so your body works really hard to maintain what's called homeostasis. You may have heard of that word. So homeostasis, and with all of these different things, and pH is a big one. All right, and so it's important to keep it within that range. And so this picture just shows you some natural everyday substances and kind of gives you an idea of their pH, both acidic and basic. So here we have a pure water at a pH of 7, and notice here it says neutral, and it says H+, and the H+ has these little brackets around it. You guys know what these brackets mean? Okay. Yeah, I learned last hour that most people didn't know. The brackets mean concentration. So when you have H+ with brackets around it, you read that as concentration of H+ ions. All right. So this is the concentration of. That's what those. So at neutral, pure water, remember it can dissociate into H+ and OH negative ions. They're an equal concentration in pure water, so that's what they're showing you here, equal concentration. And then notice what happens with the pH scale. As the pH scale goes down here, we go from pure water, urine, it talks about rainwater. We'll talk in a little bit here about rainwater naturally is slightly acidic. And so on and so forth, all the way to battery acid. So this is increasingly acidic. And what does that mean? Remember, acids release H+ ions into solution, so your concentration of H+ ions is greater than your concentration of OH negative ions. And then when we go from neutral to more basics, we have oven cleaner down here. It becomes increasingly more basic, and H+ ions is lower, the concentration is lower than the hydroxide ions. And so, so that's your pH scale. And so most things in living things are between 6 and 8 here. So you can see the human blood is slightly basic. Oh, question?
What's the most acidic thing on it?
You know what? I don't know. That's a good question. I don't know the strongest acid. I'll ask Mr. Cook and I'll let you know. See if Mr. Cook knows. All right. And then I'll double check against Google to make sure he's not making something. Those of you who know Mr. Cook, you never know. So, buffers. I said that living things is really important to maintain a constant pH, and so what we call a buffer is something that occurs in living things to help to resist changes in pH. So this is probably new for most people. So internal pH is right around 7, somewhere between 6 and 8. And it has to remain there. And the thing is that we take stuff into our body. We eat things, we drink things, we breathe in things. These are different molecules, different chemicals that can change the pH in us. And so therefore, we have to have ways in which to kind of buffer those changes or resist those changes so that our enzymes can work and so on. So buffers, by definition, are substances that minimize changes in the concentration of the H+ and OH negative ions. So they minimize those. And a buffer consists of what we call an acid-base pairs that reversibly combines with H+. So it's a reversible reaction and can act as an acid sometimes and a base sometimes, depending upon the situation. So there's one other thing you need to get out to, I guess, tell you. And yesterday you picked up the buffer. There was a single sheet that said buffer example at the top. We're going to go through that example right now to help you to understand this concept. Alright, so we're going to talk about this buffer example. This is a reversible reaction, so to illustrate that, we're going to do this. We're going to go in two directions. And what is this buffer example? What is it called? Really, this is the carbonic acid buffer So what are these things? H2CO3, this is your carbonic acid. And we go from left to right. Carbonic acid can break down or dissociate into two ions, this negative and positive ion here. So this is called your bicarbonate ion. And then H plus we should know is our hydrogen ion. But if you want to make that, you can make that as well. So this is hydrogen ion. So that's why it's called carbonic acid, because it's acting in solution. If it goes from left to right, it will act as an acid by, remember, definition of acid, releasing H plus ions. So it's acting as an acid. So then let's look at if it goes in the reverse direction from right to left, so in the direction towards the left. It reforms carbonic acid. So the H pluses combined with the bicarbonate ion to form carbonic acid. And so therefore it can take, that's going from right to left, H plus ions out of the solution and reform carbonic acid that can go in either direction. So let's look at this then. Let's go from left to right. Carbonic acid breaking down into the bicarbonate ion and the hydrogen ion. If this is in your blood, in what situation, this is supposed to buffer changes in pH. And so what must be happening to the pH or the concentration of hydrogen ions if the buffer in your blood went from left to right? In what situation, what must be going on in your blood for this buffer system to go from left to right and release H plus ions?
Probably too basic.
All right, if it's too basic, what's true about the hydrogen ion concentrations? They've gone up or down? Basic, the hydrogen ions go down, all right? And so if the hydrogen ions go down in your blood, the concentration, would it make sense then that you would want to replenish them? All right, yeah, and so therefore the carbonic acid will release H pluses. So I'm gonna put over here by this arrow here, I'm gonna pick a different color here. I'm gonna make it, I'm gonna put this in this direction. This is a response to a rise in pH. If you have a rise in pH, what happens to your hydrogen ion concentration? Rise in pH, it goes down. So I'm just going to put a down arrow for decreased. So you have a decreased hydrogen ion concentration. And so the buffer system will go from left to right, releasing H pluses and replenishing and bringing the H plus ion concentration back to what it was. On the flip side, if we go from right to left, the H pluses rebond to the bicarbonate ion and form carbonic acid. So in this case here, you're taking H plus ions out of the solution and reforming carbonic acid. And so this arrow to the right, different color here, this would be in response to what? Yeah, to a decrease in pH. Which means, what happens to the hydrogen ion concentration? It gets too high. It gets higher than the hydroxide ion concentration, so we're going to take out H pluses, bringing the concentration back to what it was. And so this kind of oscillates back and forth depending upon what's going on in this case, the blood. And so if we look here, I'm going to draw a picture here and just go through some examples here to kind of help people to visualize what's going on here. So it's as if a base is dissolved in water. So I give an example of sodium hydroxide. So water was equal concentrations of H pluses and OH negatives, right? So I'm gonna go ahead and draw a couple of H positives and OH negatives to show, okay, this is my pure water. I have equal concentration, so pretend like you have a little glass of water here or something like that. And that's your pure water. Now I'm going to add sodium hydroxide. I'll pick a different color here. So sodium hydroxide is Na plus, and can you guys see this purple, okay? Yeah, okay. OH negative. So that's the ionic compound there. And so when we add that to water, it dissociates. So you're going to have Na plus and OH negative. So pretending like we're adding that to water. And that's what happens. So now, by adding sodium hydroxide to my pure water that had a pH of 7, equal concentration, added sodium hydroxide, now what have I done to the hydrogen ion concentration? By adding sodium hydroxide. Hydrogen ion concentration went down, all right? I didn't take any hydrogen ions out, but by adding OH negative, in looking at the relative concentration, I have decreased it. So I'm going to write here that I have decreased the H plus ion concentration. Or what have I done to the pH? Have I increased or decreased the pH? I've made it become more basic, which means then that I have increased the pH. So that's what I've done. I'm just using up and down arrows for that. All right, so if this were, let's pretend like this is your blood. Your blood is not pure water, but just for simplistic sake here, if this has happened to your blood where you've got now a decrease in H plus ion concentration, or the blood has become more basic, going back up here to the carbonic acid buffer system, in which direction will the buffer system go? To the left or to the right? Left or right? I'm going to be talking to the person sitting next to you. Come up with a.
She wrote a decrease in H plus she was saying to me at the top.
I remember what specifically
Like the buffer thing that she wrote for me, like it says that that's the rise of pH, which is what happened was when you added it.
All right, let's come back together here. So who wants to share? Will it go to the left or to the right? It will go to the right. Why does that make sense? What do we want to do here? So we've decreased the hydrogen ion concentration, so our goal then is to increase it again, right? So it goes back to where it was at. So we have equal concentrations of H pluses and OH negatives. So we want to increase the H plus ion concentration to get it back to equal. Which direction is going to increase the H plus ion concentration? Left to right, because when carbonic acid breaks down into the bicarbonate, it also releases H pluses, which is going to bring the H pluses up. Does that make sense? All right. And so we're going to write that. So the buffer system. Will go to the right.
Please excuse the interruption. At this time, any student taking a shuttle to the junior high school after their second hour class should be dismissed. Thank you.
And so let's write what's going on here. When it goes to the right, what's going on? The carbonic acid dissociates or breaks down into its respective ions. diminishes what? The hydrogen ions. So they are equal in concentration again. To the OH negative. So if I were to draw that into this picture, so you have in the blood, there's naturally the carbonic acid. And so what will happen is it'll break down into the bicarbonate ion and H plus. And so now you will, that won't be present anymore. Now these two ions here, and it releases the H pluses, and now we have 3 to 3, all right? And so therefore, bringing it back in this case to the pH of 7 will be off. Does that make sense? Okay. And so then on the flip side, let's go through an example with acid. So again, I'm going to start out with pure water again. So equal concentration for the H pluses and the OH negatives. And for the acid, I'm using hydrochloric acid. So this is H plus and Cl negative here. It's hydrochloric acid. So when you add hydrochloric acid to water, it dissociates into the H plus ion and Cl negative here, the chloride ion. And so that's what's going on here. And so in this case, now what has happened to the hydrogen ion concentration? It has increased. So we've increased the H plus concentration. Or another way to say that, we did what to the pH? It goes down, pH goes down. So now, what do we want? We want to bring it back to equal concentrations here, for which is what it started out with for pure water. So what do we want to happen to the hydrogen ions concentration? Do we want it to go up even more? No, because it's already gone up. It wasn't equal concentration to the OH negative. So now we've got higher concentration of H pluses, so we're going to want to bring those H pluses concentration back down, right, to where it originally was. Because that's what a buffer does, is wherever, in this case we're starting out with pure water, equal concentrations of H plus and OH negatives, that's what buffers do, is they minimize changes in pH. So if the pH started at 7, we're going to minimize changes, and so if it gets to, if the hydrogen ion concentration goes above or below equal, then we're going to make it go back to being equal. And so therefore we want the H plus ion concentration to decrease. So how in the world will we do that to make the H plus ion concentration decrease or go back to normal? Well, we could add OH negatives, but that's not what this buffer system does. This buffer system, there is adding no OH negatives. So the only thing we can do to bring this H plus ion concentration down is to take away H pluses. So remove the H pluses out of here. So therefore, what removes the H pluses, in which direction? The left. The H pluses will rebind to the bicarbonate ion and form carbonic acid. When it does that, it takes the H pluses out of the solution and brings it back to equal. So let's write that down. So the buffer system will go to the left. And what happens when it goes to the left? We write it in words. So we have the bicarbonate ion accepts the H pluses out of the solution. All right, so bicarbonate ion. Out of the solution. And then they will become equal, so then they do. And I use the example with pure water, since we're talking about pure water, having a pH of 7 and this buffer system, but buffers, I don't want you to think that buffers always make a solution have a pH of 7. A buffer just resists changes in pH. So if you have, this is only one type of buffer, there are many different types of buffer. If you have a buffer in a solution of a pH of 5.2, there are buffers that will then maintain that 5.2, so that 5.2 solution, if it gets to acidic or basic beyond that 5.2, will work to bring it back to 5.2 its original, pH. And so that's how buffers work. Very, very important in living organisms to maintain homeostasis in with pH. And so let's go back to the notes here. So I use the example of pH and how acidic and basic a solution is very important for internal processes going on, so inside of the body and so on. That also can, things that go on outside in the environment can also affect living things. So this is just the threat, this is a threat of acid precipitation. It kind of goes with this. Precipitation is basically anything water-based that falls from the sky. So rain, snow, fog, and it's considered acid precipitation when the pH is lower than 5.6. 5.6 is acidic, right? 5.6 is below a pH of 7. So notice that if the pH, let's go back to here, I can show you. Notice here the pH of rainwater is naturally acidic. All right, so it just has to be more acidic than the 5.6. And the reason why rainwater normally is acidic is that water in the atmosphere comes into contact with carbon dioxide. There's lots of carbon dioxide in the atmosphere. When water comes into contact with carbon dioxide, it actually can react and form carbonic acid, the same acid we just talked about that's in our blood. And so therefore, the rainwater that comes down naturally from the sky is slightly acidic because of the carbon dioxide in our atmosphere. The thing is that, and why it's not considered, and that's why it's not considered acid precipitation until it gets lower than 5.6. So then what happens is you can get precipitation lower than 5.6 by all the chemicals that we put into the atmosphere. So there could be pollution. Also, we increase the quantity of carbon dioxide in the atmosphere by burning fossil fuels and things like that. And it makes the precipitation more acidic than naturally, what it is naturally. And so acid precipitation is caused mainly by the mixing of these pollutants with water in the air. And it can damage life in lakes and streams. So how can acid precipitation damage life in lakes and streams?
It changes the pH, and a lot of people living there can't deal with that. They don't have the buffers for it.
That's exactly right. And so they have, they can live with their external environment, the lakes and streams, within a certain pH range and can't adjust if it becomes too acidic, the lake and so on. And so that's aquatic life. And then what other type of life would be affected by acid precipitation? Changing the pH and plant life. By how would acid precipitation affect plant life?
The acid goes into the soil and the plants.
That's exactly right. So that water that's acidic is going into the soil, changing the pH of the soil, kind of changing the chemistry of the soil, and the roots are taking in that water and therefore changing the pH inside the plant and so on. And so plant life can die or have a hard time surviving, which means then can it affect other organisms then? It can affect organisms that eat the plants and so on and so forth. So it's not just changing pH and keeping internal pH constant, but also the environment, plants and animals are adapted to certain levels of pH. And so that last one is the effects of acid precipitation on soil chemistry. And so those different forests that provides habitat, not only food, but habitat for organisms and so on. All right. Okay, so tomorrow, I'm going to give you like a 3-question little quiz over chapter 3. Kind of the gist of it is going to be about the water properties. I'm not going to put the pH stuff that we just talked about because you haven't had a chance to like kind of digest that yet. So just to get you to study it a little bit here as we go on. So it's not a big quiz, but just something to get you to look over the material. Okay? All right, well, we are going to start chapter 4. So, chapter 4, going on with more chemistry. We have 7 minutes. All right. Do a little chapter 4. Like I said, chapter 4, the gist of it is the chart there with the functional groups that you do for homework. But we're going to look at it. Basically, the whole idea is looking a little bit more in depth into the chemistry of living things, and that we depend upon carbon as our main atom, and a lot of the macromolecules and things that we're made up of are carbon-based molecules. So lots of water. We talked about that, 70 to 95% water inside of our cells, and the other class of molecules that is next most abundant is carbon-based molecules. And so carbon molecules, we have a wide variety of them. We're going to talk about why that is, the fact that carbon can bond with 4 different atoms, and those carbon molecules form different classes of molecules, proteins, carbohydrates, DNA, and so on. It's very, very important to do different things in our cells. So the study of carbon-based compounds is called organic chemistry. Organic compounds range from simple to large ones. Most contain hydrogen atoms in addition to carbon. Carbon and hydrogen are very, very important. They used to think this concept of vitalism, the idea that organic compounds arise only in organisms, that was disproved when chemists synthesized organic molecules in the laboratory, and that this natural phenomena is governed by physical and chemical laws, and we use those to synthesize those chemicals in the lab. And we're going to talk about this later on in the course, but this is the apparatus that they actually use to synthesize organic compounds in the laboratory. And so we'll look at that a little bit later. All right, so let's talk about carbon, just a quick little review about carbon. So an atom's electron configuration gives it the atom its characteristics. It's key to an atom's characteristics. Determines the kinds and number of bonds that an atom will form with other atoms. So carbon has, am I going too fast? Am I good? Carbon has 4 valence electrons, and therefore can bond with 4 other atoms. It can make 4 covalent bonds. They call this tetravalence, tetra meaning 4. And therefore large organic molecules can be formed as a result of that. So if you have molecules that have more than 1 carbon atom, so multiple carbon atoms, each carbon bonded to 4 other atoms has a tetrahedral shape. This you should remember from chemistry. Yes, shapes. Remember that? No. However, when 2 carbon atoms are joined by a double bond, the molecule has a flat shape. And so, this picture here shows you that concept. So here is methane, CH4. This is how you would draw the structural formula of the bonds. Each one of these, remember, represents a shared pair of electrons. It's a covalent bond. But when the atoms actually bond together, the carbon here is in the middle, they actually don't look like this. it looks like this tetrahedral shape. All right, so that's what it means by the carbon bonded to 4 different atoms has that tetrahedral shape. And so the bonding and the shapes of the molecules, so this has C2H6, this is what it looks like on paper, and its actual shape. And ethene has a double bond, so this carbon is still making 4 bonds, but 2 of those 4 bonds are going to 1 atom. And when there's a double bond, the molecule is flat versus like the tetrahedral shape up here. And so the shape of these molecules, we're going to learn a big theme in biology is that shape determines function. So the shape of a molecule determines its function and what it does. And so therefore, shape is really important, and you can't see that sometimes from the structural formula, all right? And so this is where we'll so come on down and get your phones.